Okay, so we are going to start off with a bit of a review of just, finding some points on a coordinate plane. So I'm just going to run through these really quickly. And you can pause this, try these on your own, and then go ahead and press play and check to see that you were right, okay? So R is 4, 2. S is -4, 3. T is 5, -3. U is -2, -5. Number 5 or V is 7, 0. W is 0, 5. X is 0, 0. And Y is at -3, 0. Okay, same thing here with these four. A is at 4, 2. B is at -3, 2. C is at -2, -1. And D is at 3, -2. Okay, let's answer a few questions about points on a coordinate plane just to kind of refresh our memory. We're going to go ahead and scroll to the bottom of the page. So right underneath those two pictures, we have these questions. What common property describes the coordinates of the points on the x-axis? So all these points on the x-axis, what do they all have in common? Y is 0. That is what they have in common. So we go left or right some amount. We're either going to go forward some amount, right? Or we're going to go backwards some amount. But either way, we're not going up or down at all. We're just staying right on this line no matter where we're going, left or right. And so Y is always 0, okay? By the same token, in the other direction, if we are just thinking about points on the y-axis, the same thing is going to happen. We're either going to go up some amount or down some amount, and no matter what we do, we are not going to go left or right at all. So in this case, x is 0, and so the x-coordinate is always 0, and the y-coordinate is just telling you how far up or down you're going to go, okay? Describe the signs of the coordinates of the points that lie in the upper left quarter of your graph. So if these are my quadrants, and I want the upper left coordinate, quadrant, then I'm going to go from the center, from the origin, I'm going to go backward some distance, whatever it is, so that's a negative, and then I'm going to go up. So I'm going backward and up to get into this quadrant. So negative and then positive. Okay. Describe the signs of the coordinate of the points that lie in the lower right quarter of the graph. So lower right down here means from center, I'm going to go forward, that's positive, and then I'm going to go down, that's negative. So that's how you figure out what these signs are in each of the quadrants. Let's move along to the next page where we are going to start talking about linear equations and functions. Okay, so the first thing we're going to do is kind of describe independent and dependent variables. So this says, describe the difference between independent and dependent variables and use the linear equation y equals x plus 3 to help you explain. So this is the example. And I need to know which one is the dependent variable and which one is the independent variable. So the independent variable is the x value, because I can pick whatever I want to plug in for x. Okay, I can choose any value to plug in for x. The y is the dependent variable. So independent is x, dependent is y, because it depends on what I chose to plug in for x. Okay, depends on what I chose for x. So usually the independent variable is the x, and usually the dependent variable is the y. That's not always the case, but usually that's what happens, okay? Now, I know some of you are saying, well, I could just choose any value I want for y and plug it in and solve for x. Yes, you could, but the fact that the y is isolated all by itself means that I'm just plugging numbers in here to x, one after the other, and adding 3 to it, and it's telling you computations are located in this equation, so it's a line that goes on to and how do you write the solution statement which usually relations and functions. So this is how every square is a rectangle. The relations are general, and the functions are more specific. The relations is just a set of every square. That set of ordered squares doesn't have to form any special shape. It is just random all over the place. The domain is of the relation is the dependent variable. Independent variable. The domain is the independent. That is the second. And the range is the dependent variable. Okay, and that is the set of y values. A function is a special kind of relation, and that is where now on the right side they become more specific. So these were just any old points anywhere. They didn't have to form a special shape per se. But a function is a special kind of relationship where each x value is paired with only one y value. Okay, that's a very specific situation. We're going to talk a little bit more about whether something is relational. So, let's talk about functional notation. How do you write something that's functional to one? So we can take every linear equation we want and we can rewrite it as a function. So what that means is functional notation is written like this. This is the notation we use. And it replaces the y. Okay, it replaces the y, and here's how we do this. F of x. Or we could say a function of x. Okay? And it's used when we need to plug several values in. Why do we use functional notation when we need to plug in several values for x? Here's why it's important. So right now, if I were going to plug in a bunch of values for x, I would have to plug it in here, multiply it by -2, and then add it to the other side in order to cancel it out and get y by itself. And I would have to do that manipulating of the equation every single time I plugged a number in for x. So instead, we solve for y one time. So So we isolate the y one time, and then we replace it with the functional notation, and then it's just a plug and chug kind of situation. Let me show you. So instead of having to, every time I plug a number in here, calculate it and then move it to the other side of the equation to get y by itself, I'm just going to get y by itself right now. So here's y, and I have to undo negative 2x. I'm going to add it. This is my equal sign, so that's my balance scale, meaning that if I add 2x to the left, I have to add 2x to the right. My zero pair will cancel over here, and I have y equals 2x minus 3. And we always like to put that x term first. I want it to be similar to y equals mx plus b, where the x term is first. And then we're going to replace the y with f of x. So now we say the function of x is equal to 2x minus 3. And this is a lot easier to plug a number in, multiply by 2, subtract 3, multiply by 2, subtract 3 every time, and you don't have to go through all of this manipulating each time. So this is the reason why. Now, right now you're thinking that's not a big deal because this is not a long involved algebraic equation. But if you're dealing with a very long involved algebraic equation, you're figuring interest rates or something that involves a lot of calculating, and you want to simplify it as much as you can so it's more of a plug and chug situation. Okay? Let's go ahead and do that with the second example. Again, there's my balance. Whatever I do on the left, I want to do on the right. I have my y value right there. It's a positive y. So all I have to do is isolate it. I'm going to undo positive 2x by subtracting 2x from both sides of the equation. Now I have a zero pair, and y is all by itself. Remember, I want the x term first. So negative 2x, and that's a plus or positive 7. And replace the y with f of x. And you have your equation written in functional notation. Plug values in for x, multiply by negative 2, add 7 every time. Okay? We're going to practice doing that a few times with an equation, just so you can get a feel for what that's like to just kind of be able to manipulate the equation one time and then plug and chug several times. We're going to do it with these two examples. Okay? To find a set of solutions for a linear equation, here's what we're going to do. First, these are the steps. And in the first example, most of it is done for you. Okay. In this first example. In the second one, you actually do have to solve a little bit. It's not done for you. Okay, so you have one where it's done for you and one where you have to manipulate it a little bit. Change the equation to functional notation. You can see that's already done. Functional notation, check. Make a table, choose some values for the independent variable. That means for the x done. They already did domain is x, so they've already chosen those for you, and they've already placed them in the chart for you. Calculate the dependent variables. They didn't do that yet. That's what we need to do. We need to plug in and get our y values out, and then we need to write the solutions, and this is the column where we write our solutions. So let's try it. We're plugging in negative 2. F of negative 2 equals 2 times negative 2 minus 3, or negative 4 minus 3, or negative 7. So when x is negative 2, y is negative 7. F of negative 1, 2 times negative 1 minus 3, negative 2 minus 3, or negative 5. When x is negative 1, y is negative 5. You might pause this and finish the chart and then come back and check your answers when you're done. Or you can just keep trucking along with me if you'd like. 2 times 0 minus 3, which is 0, minus 3, which is negative 3. So when x was 0, y is negative 3. F of 1, 2 times 1 minus 3, or 2 minus 3, which is negative 1. When x is 1, y is negative 1. And then f of 2. So 2 times 2 minus 3, or 4 minus 3, which is 1. When x is 2, y is 1. So we have all of our solutions calculated. When x is these, y ends up being these, then we have this solution. The second example is not done for us because y hasn't been isolated for us yet. We actually need to do that. So 2x plus y equals 7. Here's our y term. We need to subtract 2x from both sides of the equation. Y equals, remember I want the x term first, negative 2x, and that's a plus 7 because it's positive. That is what goes in your chart. Just remember to replace the y with the f of x, and then the negative 2x plus 7 goes in there, and you're going to test all of those x values, get your y values, and then write your solutions over here. Okay, so f of negative 2 equals negative 2 times negative 2 plus 7, or 4 plus 7, which is 11. Okay, so when x is negative 2, y is 11. F of negative 1. When you plug in a negative and you're multiplying by a negative, don't forget this becomes positive. 2 plus 7 is 9. So when x is negative 1, y is 9. F of 0, negative 2 times 0 plus 7, or 0 plus 7, which is 7. When x is 0, y is 7. F of 1, negative 2 times 1 plus 7. Negative 2 times 1 is negative 2 plus 7, which is 5. When x is 1, y is 5. And last one, f of 2, negative 2 times 2 plus 7, or negative 4 plus 7, or 3. When x is 2, y is 3. So there's your solution. That's the solution set. Okay? Now, the next question is asking you what the graph of a linear equation looks like. And that's not a trick question. It is just simply, what does the graph look like? It looks like a straight line. Okay. How can I decide if the ordered pair negative 2, 16 is a solution for the equation 2x plus y equals 12? You decide by testing it. Testing it. If that's the x and that's the y, we should be able to plug them in. 2 times negative 2 plus 16 equals 12. And we should be able to see, does it actually equal 12? Negative 4 plus 16, or 16 minus 4. So 12 does in fact equal 12. What does that mean about the point negative 2, 16? It means that it is a solution and also a point on the line. Okay. Check to see if 3, negative 2 is a solution. Let's try it. So here's my negative 2, and 2 times 3 minus 5. Let's see if this works. So 6 minus 5, which is 1. Negative 2 does not equal 1. What does that mean about this point? Not a solution. If it's not a solution, it is also not a point on the line. Okay, it is also not a point on the line. Okay.